Thank you. Thanks for Winky to invite me. And also, I just want to correct, I now left the VA last year, and Mei Chung now is the acting director for the VA Coordinating Center. And Winky wanted me to report some work that I collaborate with Bilan Li and also Senghua Kelly Fan, and on the early phase cancer trial design. And I think it's very appropriate because both of them at one time point were faculty at this university, and also I believe Bilan is Singaporean. And so I report some what we have done in the past in the early phase cancer trials. So I just outline a little bit about introduction, and then I talk about this curve-free Bayesian decision theoretic designs and how we extend to the drug combination. And the later part I talk a little bit about frequentist point of view about parametric stochastic modeling approach and some discussions. And I get nervous a little bit about talking about Bayesian because, the one thing that, many things maybe I didn't learn well, but one thing that definitely I didn't learn from Berkeley is the Bayesian statistics. So anyway, whatever. Okay, so there are some maybe I didn't went through. So basically I want to talk about cancer treatment types. There are, at least exclude gene therapy, there are cytotoxic treatment, typically represented by chemotherapy. So in that case, the more you put to the body, the more likely you kill the cancer cells. So the goal is trying to reach the highest possible dose. And then there's recently those molecularly target therapies, and people no longer believe that the more the drug you put in, the more turn on the activity and the more efficacy. So it's no longer really correlated with those, the benefit of the treatment is no longer correlated with those. Yet the more the drug you put in, still the more likely you get more toxicity. And then also immunotherapy is more popular now, and it's really not, so the first one is really kill the cancer cell, the second one is working on the cancer cell, but the third one is really working on the body to develop the resistance system. In that case, it may no longer to be the better, not only the more of the drug you give, not necessarily increasing your efficacy, but maybe getting start to harm you at some time point. So really the searching for those become very interesting, and the people are using more combination therapy nowadays because the tumor is heterogeneous, and there's also overlapping toxicities when you put combined treatment. And sometimes you want to see one cytostatic and one chemotherapy to make sure you overcome the tumor resistance. So that's what basically the play field that we're looking for. So looking for one treatment, one dose that basically, this is a meta-analysis for one of the chemotherapy that you show the dose response, this side is toxicity and this side is the dose. And as those increase, we see the toxicity increase. And then normally we want to look for some kind of maximum tolerable dose, so MTD. So that's where you want to limit your dose, go to the phase 2. And so in early phase that done in the university, mostly we work on the early phase 1 and sometimes phase 2. The university rarely go to phase 3. And so the phase 1 usually focus on the safe dose and PK/PD type thing. And the phase 1 also recommend those for, basically we want to recommend the dose to phase 2 trials. And sometimes the university runs some simple phase 2 trials and focus on the proof of concept, and then the deliver the product to the drug companies to develop. So in terms of recommended phase 2 dose, there are different ways you can recommend dose here. One is MTD, which is maximum tolerated dose, or MED, maximum effective dose, which it's not get to the tolerate level, but maybe effective dose based on some kind of signal or combined phase 1-2 trials. And also optimal biological dose, which is more based on the biomarker. And there are ways that do that. Earlier people described there are rule-based approaches that like 3+3. It's very intuitive, ad hoc, and very popular. And no matter how hard you try, physicians still want to use them because they feel they can control it. And there are also model-based approach like continuous reassessment method and all these various versions. And it's being proven better than the rule-based, but still, there are a lot of hesitation to use. Partially, they feel they lost the control of the process. As Steve Singh mentioned, it's not a bad thing, but for physicians, that's really get them nervous, right? So, but we still need them buying in order to use it. And also, there are different ways. You can do frequentist version of the CRM or Bayesian version of CRM. And so today, I just talk about curve. So one thing that when we use a CRM is a logistical power model. There are some set of parameters that you need to talk to physician in order to start to use. And those numbers always like pulling teeth. It's very hard to get from them. And so that's where we start to think about some maybe easier way that they feel more comfortable and a curve-free way. And also, of course, Boeing is one of the way very nicely to do. But we want to see also, hopefully, the dose that we're doing will impact on the dose that's not in the experiment. So influence through some kind of relationship. So that's where we call the curve-free Bayesian decision theoretical design. So not the Bayesian, I just put this cookbook, and there's, we need these kind of components here. One is a working model, and we have to define our starting cohort, and we have to define the utility function, and then we can decide using the decision rule to select the dose and the stopping. And so that's how we select the dose and recommend. So this work was done 5 years ago, and with Kelly and Yugen Wang from Australia. So here we starting from a very basic model. So again, toxicity response is binary, so it's a Bernoulli distribution. And the probability, Bernoulli probability follow up prior is beta prior conjugate. And therefore, you can estimate the average toxicity rate based on the beta function. And so for observed, for a dose, if we observe, we have a cohort, depending on how often you update, right? So if I have NI patients and of the TI of them experience those toxicity, then I update my beta distribution by adding the toxic, the patient with DLT into the first parameter, and patients don't have DLT into the second parameter. So that is the basic setting. So when we ask that we start approach physicians, say, you propose this kind of dose range, okay? What's your guess for toxicity? And they usually give us some kind of meal, say, okay, this is my guess based on their animal study, whatever. And then one way that we can make sure is we can set the prior by multiply a C. The C is not critical. The C here is trying to make sure it's not bimode in the beta. Otherwise, it's moving around so hard. But it turns out, usually, if you are very sure, you can increase C very high, which is not most of the case, right? So since the mu I is kind of monotonity, if I set this way, I can make sure initially the prior toxicity is increasing function. So that's what we're started. And also the alternative, I mean, recently we figured it's maybe better because the clinician may not have that confidence. So we say, what's your lower 25 percentile? What's your up 75 percentile in terms of your toxicity? And then we can reconstruct A and B accordingly. But that's another way to do that. So the second part, which is really, I think, the difference that what we do and kind of how to take advantage that we believe the higher of the dose, the more likely you get toxicity. So the idea that borrowed really from the like survival analysis, right? So if you have dose is continuous, okay? So if the patient already experienced toxicity, then the event occurred. So you have a step functions going on. So which means that patient, if you place to the higher dose, that patient can still have toxicity. So if this patient have no toxicity at this time, you say, okay, it's flat, right? So anything that before that, that patient should have no toxicity. Okay, that's how the uniqueness of this algorithm is borrowing the information based on these prior monotonicity property. So I want to illustrate a little bit different that this is different from isotonic pooled approach. So if, for example, if I have observed in the first cohort, I have 1/3. Okay, I observed 3 patients, I have 1 with toxicity. The second cohort, I have 3 patients, I have 1 toxicity. The last one, I don't see any toxicity, for example. So now this one is not monotone, right? This one has 0 probability, and this is the 1/3, 1/3. So standard way that if you do the isotonic pooling is you first pull the recent violator, right? So you got this one first. Then this one give you like 1/7, 1/6. Yet 1/6 still lower, below than that. So you have to pull all these together to get numerator become 3 and denominator is 2. So you get a flat. If you're using isotonic pooling, you get flat data. You still borrow the information, but it's not curved. So the way that we do here is, okay, in this case, this patient, I have 1 toxicity. Literally, I add this 1 to the higher dose. So this becomes 2, this becomes 2. I borrow the patient to the higher dose. And then, so even in the dose 3, I didn't see any toxicity, but I borrowed the 2 there. So I get 1, 2, 2 into this toxicity. Now, how many patients I tested without? So for this one, they have no toxicity, right? So there are 3 patients have no toxicity. So therefore, all these patients, if they place here, they have no toxicity. Therefore, I get 6 patients here already, and they still have 1 toxicity, and 6 patients here still have 1 toxicity, 2, because I borrowed the 1 toxicity to here. Yet there are 2 more patients here who had no toxicity, okay? So I can land that patient down there, so I get 8 patients here. So now you can see the curve become flat, become curvature, right? This is 1/8, this is 2/7, this is 2/5. So it's really steep. So that's the whole thing that different from others. So this is just another way to illustrate that how we update. So if I see a toxicity, so 1 patient, I see toxicity, I update the first parameter on all the dose above that. I have no information for that patient to anything for the lower dose. Therefore, I will maintain the parameter without any change. And similarly, if I see 1 patient have no toxicity, I updated the second parameter below that and have nothing to do with the first. So if I do a group, and I can do that too. So what nice part of that is by doing this kind of update, my posterior always guarantee I have monotone toxicity rate. So I kind of effectively increase my sample size. So that's the whole, I think the main trick. The rest part is very standard. So we start from lowest dose, and we determine the size of those cohort. You can do 3 every time or 1. And then we escalate those levels until, initially we don't do anything. We just let it go, like speed up until you see the first toxicity event. Then you start to using the kind of Bayesian utility function to determine the next dose. So the utility function basically here is in the 4, you can depend on which, so theta is the target toxicity rate, and this is the posterior P, the probability. And so the utilities depend on the 2, right? The first one is below, the P, the toxicity below the target value, we give less penalty, and it's above that, we give much sharper penalty. And then you add all the patients that you have, and then you predict what happened. So you add current patient plus the future patient. So here, the nice part of beta prior is that you can write out your utility function in an explicit form, so it's very easy to calculate. We can use Excel actually to run that. And then based on that, you can determine which next dose give you the best utility. And we did look for, partially we think the beta is useful because you can calculate another expectation, the second patient and third patient. And so we did compare look for 1 patient and look 2 patients and so on. But we didn't see much gain by adding more patients. So actually in the recommendation, we're just looking 1 patient forward in selecting next dose. So there depends on the way you can just select according to the utility, or be conservative, you're just looking for adjacent dose. And so we set minimum patients that you don't want to stop too early, but also you don't want to go forever, so you can set maximum patients. And the typical stopping rule, if the first dose was toxic, then you stop, or if the future dose is too toxic, you don't want to go more. And so these are predetermined parameters. So this is graphically just show example if we use that previous paper as example. So here's how we set parameters. And these are the prior before we start, and most of them pretty flat. But then you get one patient, as it goes, you can see it's very quickly, this curve become very sharp. And so after the number of 8 patients, you stay at the one dose level. You don't move anymore. And that's where the main advantage. So in that 2012 paper, we did a lot of simulation studies and looking for the difference compared to CRM and also to see what game is. Basically, and also we did for the misspecification of prior because, again, it's very sensitive about prior. And also uniform prior, beta 11, if they're really, you don't want to put any prior information there. So overall, the performance is very well in terms of dose allocations and dose recommendations, mean number of patients needed. One thing is, because we artificially sharpened the curve, and as long as you specify the utility function right, it narrowed down the dose very quickly. So we find we need only much smaller number of patients to allocate the MTD. And also, we place most patients in the right MTD level. So, which was supposed to be a good when you have a chemotherapy case, right? But then we also investigated misspecification situation. So if you are anti-conservative, right, you overestimate your toxicity at the beginning, actually it works better because it's much harder to move to the very top because the both ends tip very quickly. But if you are really severely underestimated, that become a problem. But other than that, if anything in between, doesn't matter how you misspecify it, it will load very quickly. And also, it turned out that non-informative prior is not very good. But it doesn't good for anyone because there's no information there. So this is the first one. And then it was advantage. But then we started now, it may not be advantage. Partially, if we allocate all the patient MTD, but we don't have information for other levels, right? So if I'm doing some biological target therapy and I have everyone in MTD, I have zero information for non-MTD dose. So people now get more and more interested in the optimal biological dose, and basically this measured by some kind of marker, and so that drug has to hit that target, and the target will be measured. The target has to be altered by drugs through, then you can monitor that alter through the marker. And the tumor, of course, altered by this target, and the giving more dose does not change the improvement further. So this is what basically definition of optimal biological dose. And then so nowadays we pay more attention, not just phase 1, but we want to get some kind of signal of phase 2 to look for OBD. So there are more research recently on that. And so we want not only, I mean, if the OBD is not MTD, then by all algorithm, we don't see anything anymore. So it becomes disadvantage. So instead of a single OBD, or the other part, the OBD may be in a range. So I did talk to Ying Lu the other day, and he said maybe OBD should be the lowest one. That may be fine. But anyway, so we may want interesting, not just the one dose, but maybe we want interesting a range of the dose that can achieve some kind of activity. Okay. So we borrow some kind of idea about phase 2 trials that you have historically an acceptable level, but you have some kind of acceptable level beyond DOT. And so there may be multiple doses above that. So you're not looking for one dose. And So here, if EI is the probability of response, and then the goal here is trying to find. So first of all, we want to make sure that the dose will not hurting patient, right? So there's admissible dose range that below the MTD. And secondly, we want to accept the dose that efficacy is beyond the target goal, but yet still within the safety dose. And we kind of impose for one-dimensional case, you can think we impose it at an interval. So we don't search for individual dose randomly. We want the dose within the range of interval. The notation is, say why we put this notation, that the goal is trying to go the combination. Okay. Now it's getting more complicated when we get combination because you're really looking for islands that connected, it's not just single island. So somebody criticized, say, why you want to do that? Because you have disjoint those, right? So maybe the islands on two sides, they don't join. There's a valley in between. Fair, I don't know how to do that. But I feel that you have to put some kind of constraint there. Otherwise, you get single dose peak up and randomly. So anyway, so that's the goal that we want to see. We want to find a B. And so we're beginning, when I do the first thing, because we don't use a lot of patient to allocate MTD to start with. So we're kind of thinking about two stages. We're starting to quickly find the up bound, so that we have kind of an admissible set narrowed. And meanwhile, when we do this, we still observe the effect size, right? So the first round, once we finalize MTD, we can see if there are any, if there's no A, of course, don't talk about that. If there are any B possible. And most likely, there may be not enough B there. So then we say, okay, we want to, so first of all, we find A, and then we say, okay, here's the number of patients. Here's the number of patients tested with some kind of activity. So we assume it's a binomial distribution. So that's how we search for B here, okay. So we look for all possible intervals that in the one dimension below that. And then I calculate this binomial likelihood function. And we treat everyone else as one group, and this interval as one group. Now I'm looking for the maximum likelihood function that separate the data. But meanwhile, the interval has to have this property that above the pi. So that's where we start to search for the B. And another way that we can do that too is if I specify unacceptable pi 0, then I draw a line between pi 1 and pi 0. Then I look for the interval that best separate the interval, deviate from that line, and using that to looking for my B. So these are two different ways to do that. So initially, the B may be empty. In that case, we're going to randomly assign patient to the admissible pool to get more dose information. But once I get some kind of signal of B, I start to look for patient on the boundary of the B, early and late, before and after randomly. And then until I use up all my patients, or until that, beyond that is confident enough. So in that interval, you're going to make sure that we get the effect size with a certain confidence. And we never stopped, actually. So this one, we use a simulation based on one example by Zhang and Li, who published last year in the Statistics Medicine. And in their setting, basically, they look for, it's the same setting that they look for the effective dose below the safety dose, but they look for efficacy, so like phase 1 to arm. And they're assuming is the efficacy is unimode, that there are only one peak. So then therefore they randomly locate the peak, the maximum value, but then they estimate all any violators in kind of forced regression way, non-parametric regression way. And so we use their scenario as our example. So we simulate 5,000 times for each data. And so every time we just say the trial will not run more than 50 patients. Because if there are more than 50 patients, we usually don't do it at the university level. And so we assume the toxicity rate is 30%, and the efficacy rate is 30%. So in the MTD, the Bayesian one, we have some kind of like threshold, right? You have to do the slope with threshold. So we put that as 0.03. So it's either 0.27 or 0.33 in order to get the penalty. And Oh, no, that in order to stopping, that's delta that we use to stopping. And also we take the unacceptable at 0.02, and then we run the simulation and see how that procedure works. So here are the scenarios for Zhang and Li paper. So the first case is you have linear DLT increasing, but the efficacy also increase, but efficacy is beyond safe dose. So in this case, there's no safe and effective dose to recommend. And the second case, no toxicity. You never reach MTD, and also you here have 2 doses that above 0.3. And the third case is your effective dose is very earlier. Fourth case is like flat line, and this one's a flat line. Now this one's a little bit tricky because toxicity is really near 0.3. You know, it's not at 0.3, but 0.25. The other one's a little bit higher. So we did a MLE approach simulation here. So the red one shows is supposed to be the MTD that. So here is the percentage of time or simulation allocate the MTD. So most either the hit MTD or in the nearby the MTD most of the time. And so this part is the lower boundary for the interval. This is the up boundary into interval. And you can see the first scenario, we know there's no recommend dose, and therefore it's rarely select anything recommend. And the second one, of course, we have the hit the right. So the green is the right, the true lower bound, and this green is the true up bound. So we hit quite a lot, and this one also is very high, and this is reasonably high. And so on average, patient toxicity is like 20%. Patient increase in toxicity in the first case, and 12 patients in the third case, which is not, they don't have MT. This one had no MTD, it's 13%. And these are the average patients that have efficacy response. And you can see that the one with MTD, they have much higher, and this one's much lower. And so this is the percentage of time there's no B. So the B is empty, you don't recommend anything. Of course, first one is 92%, you don't recommend anything. And the other percentage is lower. And now once you recommend a B may not be right? So the last column is how many times the B actually being right. And they're all above 50%, and some of them 70%. So this is the first thing that we try. And we really want to do is to do the 2-dimensional, but we find it's very hard. Partially the boundary, as Ryan mentioned, when you search for that, you may end into one direction boundary, and the other part become very hard to search. But anyway, so take-home messages that we propose this curve-free Bayesian disease theoretical design that take advantage of monotonic dose toxic relationship, and we feel it's easy to explain and easy to implement to the clinicians, and we allocate MTD pretty fast. I think maybe sometimes we don't know if they're artificially because we force the curve to the very fast. And we also start to explore the OBD option using that. And there are drawback, and people maybe not put too much confidence for the toxicity estimate on both ends, because it's very extremely assumed. Now I move on, maybe talk a little bit about the combination. And so we know that more and more we start to combine the drugs. Now in the combination space that Guosheng and Ying Lu already explained, that you have more choices and more broad space. And so partially in this case, we have only, we still have a small number of patients, and we have much larger searching space, and we have some kind of partial ordering, and the possibility for more than one MTD combination. So here, what we do here is we kind of copied what we proposed before here. Is we put Pij as the toxicity rate, and we assume there's some monotonicity relationship, which is partial relationship. And one approach you can do is one-dimensional, right? You fix one dose and go there, or you can fix another dose. So what we do here is we just, again, extend the same model. So we have assumed the Ij as the dose combination. You have binomial response for toxicity, use a beta prior, And the only difference is that monotonicity is based on the partial ordering. And so there are different ways you can define partial ordering. One is strict ordering, which means the second dose, at least one of the doses need to be increased. But you can do also diagonal ordering, which means the sum of the two doses is more than the other one, okay? So the model, the working model here is the same. We just want to make sure that, first of all, we want to specify how the prior being set. Now, here in the two-dimensional case, sometimes we do have the toxicity information from a single drug, okay? So in that case, you can, using this kind of, assuming they're independent and you multiply. But I want to warn people, this is not right assumption of independence, because this is the dose actually depending. This is the other dose is 0. So it's not marginal distribution, but we put that as an initial step. So we do the same thing. The only difference here is we only update the doses on the partial order. So if I have toxicity, I update all the partial ordering that the dose, this is wrong, I think. Yeah, the dose above that, so this should be wrong. And this, anyway, so it's above that, you update first one, below that, you update second one. And so we want to make sure the partial order is reserved. So this is just some situation to show. So, and we do the same thing as starting cohort. We do the same utility function, and then we select ij based on the maximum utility, either surrounding dose in this case, or you can jump. But most time we don't jump, right? So we only do the surrounding dose. And we do the same sample size limitation, and we did the identical idea. So this paper was published 2017 in the Journal of Biopharmaceutical Statistics. And so this simulation shows most patients actually allocated near the MTD level. And we, again, because the steepness, we get less number of average number of sample size to reach the MTD. And the most time, in the two-dimensional case, sometimes you don't recommend MTD. For example, you run CIM, you didn't find any MTD. And in our case, the probability of recommend MTD is higher than the other method. The case is, of course, if the dose is on the corners off the curve, if the MTD is some kind of off diagonal far away, and then it doesn't move very fast, so you don't gain a lot of efficiency. So this one just want to mention that we need new designs for phase 1 combination trials. And so we extend this idea to the new trial. We thought originally we expect more because the dimensions are higher. Artificially, alter the space, you'll gain more efficient, right? You think that it will be narrow down your search space much faster. But there are also risks there that on the off diagonal become harder to move. And we are working on the joint phase 1 too, and as I explained, we didn't do very well in the joint 2 space, but at least we did simulation proof concept of single dimension. So we're still looking for the combination for joint. So I think those are the 2 Bayesian things that I'm gonna report. And then I want to talk a little bit about some new thought, and actually I presented JSM last year of this idea. So basically, if we look for the current MTD studies, we are always focused on descriptive model, right? So we in the model, we rarely build a biological relationship of drug, body, and disease. So the parameter is those versus what we observe, but not internal how they related, right? And so in the early phase trials, we always have PK/PD information, but rarely we use them effectively in our design. I know people are interested in that. And the current paradigm is very difficult to extend. I mean, we do well for 2 drugs. What if we have 3 drugs? And the other day we talked about also strategy that you want use 1 drug first, then your 2nd drug and 3rd drug, or you're spacing that. Now, if those all putting it together, it's very hard now to use this kind of descriptive way to deal with that. So really what we want to do is integrate biological meaningful parameters in this design. And that will be basically, to me, I think it's dose, which we observe, we're given to the patient. But really what effect is the exposure, right? It's how much dose in the body. That's where the driven process. So this is the link that we haven't really emphasized that. And all the events that we are interested in is a function of exposure. And so it seems that we skip this. We really model this to those to the event that we're interested in. So this is the old paper in the, published a long time ago by Qinlang Chen and Paul Confolti from Berkeley. And what they did is they built a survival model for cancer, the time to tumor. And basically, their basic idea is that the hazard ratio, right, the tumor mortality intensity is a function of a cumulative effects of individuals' continuous exposure to the toxic material in to the environment. So he defined two parameters, like simple one compartment model. You have absorbing coefficient, that you absorb the toxin, then there are also kind of discharging toxin. But what's left in the body is the one that determines the incidence of toxicity. So in their body, basically, they have two components here. So one is A is aging, because he's doing the time to cancer. And so this is the incidence rate of tumor that when it occurred is a function of age plus time, how long they exposed since age 8. And then this is kind of what he called environment. This is internal factor, this is environment exposure or something. So he said it's external exposure as in the experiment, because this is working with ED2 experiment, is homogeneous. So he take this away, and then he just focused on the first one. Oh, I'm sorry. This external is the one that I'm sorry. The internal one is the genetics, whatever. The external one is the exposure. And so because it's ED01, all animals the same, so there's no internal difference. So he took it away. And then he assumed there are two parameters. One is absorbing parameter, which is positive, and also another discharging parameter. So if I put a dose of X at time of S, okay, then this is how much they observed, theta times X during the small time ds. But then there's exponential decay. The body is trying to discharge. So by the time of t, that's how residual that you have. Of course, the patient's continuing exposure, so you have to integrate all the dose that exposed during the time period 0 to t. That's where this kind of function occurred as the intensity function for toxicity. So using this function, you can calculate the cumulative time to cancer. And then you can take a survival analysis. If you take internal effect out, it becomes this function. It's somewhat like Gumbel's, but not ideal, not identical. I think one of the parameters is different. So Rowe extended this distribution by adding a coefficient here to the scale, the exponential part. Now, this model is being fit for cancer, time to cancer with exposure of toxic, and also has been done with HIV, so viral load and the time to AIDS. So this is some kind of, the curve you can look as two-dimensional, right? One is a dose, one is time, okay? So you can fix the time and look for dose. So this is the curve by dose increasing when you fix the time. But you can also fix dose and see what time scale. So this is dose scale, is exponential distribution. And the other part that's unique here is that exposure can stop, right? So that when you expose the patient toxic, and then you stop at the time S, you no longer exposure then the cumulative function still works. You can still calculate that. And that mimic what we treat patient at some time point, we stop to treat them, right? Let them recover. So the overall the probability in that case is less than 1. So you will not always have cancer if you stop exposure. The probability will be reduced. So we just want to use this idea for phase 1 trial. Basically, okay, here's the drug that we put into, and we admit the drug in a time window, S1 and S2. And so once we do that, we have a time of T. So before the S1, there's no drug admitted, right? So there's no dose in the body. And between S1 and S2, I know this is the dose. And after S2, you don't have any new drug in the body. It's really just a discharging process as time goes, so it will get less and less in the body. So we can also calculate cumulative dose that patient received up to time T, which is in analytical form. So here everything is analytic, right? You have few parameters, which basically one is absorbing parameter, one is discharging parameter, but you can pretty much only a few finite parameters that you can control. Okay. So if I'm looking for the cycles of cancer treatment, so if I say there's a G is the length of treatment, 2 weeks for example, and then maybe the cycle is 4 weeks. You get 2 weeks break and then do that. And then, so we can write out also the cumulative dose up to time T in the body. So that's how much we have in the body. And now really what we say, okay, maybe the toxicity, it depends on how much the time of the first toxicity, dose limiting toxicity, it depends on how much dose in the body. So the more you have, the more likely you're going to experience toxicity. And that's kind of intuitive, right? Patient, when they have much more high toxicity, the physician either reduce the dose or give them longer time to recover. So that's kind of idea. So that way we can actually calculate how much toxicity in the body, the cumulative time to first to the toxicity. And so we can, assuming there, if you don't give drug, there is no chance patient is going to experience toxicity. Therefore, you can take A out, because it's purely dose-dependent activity, right? So then this B is really absorbing parameter, and the theta, they multiply the two. So So the intensity function of toxicity is a linear function of cumulative dose in the body plus coefficient. So we say no dose, there is no effect. So this is gone. The regression coefficient will absorb with the absorber parameter together, become one parameter. So this is, maybe we can also, so we can calculate the time to the first toxicity event, okay, if we know the parameter. We can change the dose accordingly. We can change the scheduling of the dose. But this is according to assuming that you have equal time window, equal dose amount, okay? So this one is one of the exponential family dose response model, right? So that in order to get no exponential dose response model, you can say, okay, instead of linear function of dose D, you can do a D square or whatever, quadratic, but still in the parametric family. Another option is to use this D to replace the dose in the conventional models, such as logistic regression for toxicity, say. I'm using this D as toxicity, right? And the theta and the tau, just two parameters, you can estimate from the data directly, or maybe we can borrow from PK/PD study, because it's very much similar to the intake and the discharge parameter. And as shown by Chang and Conforti, the conditional survival probability of time to the DLT can be derived. Basically, say I currently have no dose limiting toxicity. What is my distribution later to have? So these can be analytically formed. So the advantage of that, first of all, we can still do the standard type MTD study that we just say if the trial, phase 1 trial, the time window is T, I just looking for the dose that cumulative probability below this probability at the time of T. So it's still the same, but it's a little bit more complicated. It's no longer binomial. And that can be, if the parameter is right, if you believe that's common parameter, you can extend the T to much longer time, right? And either the same time or different time. And secondly, we can simultaneously model toxicity, maybe efficacy. I mean, this is just guess, okay? So the hazard ratio for the first toxicity event is maybe dose concentration at this time. However, maybe the treatment depends on how long the drug has been put into the body. So really, what we care about maybe the cumulative dose that received area under the curve as the toxicity. If that is the case, then you can model both efficacy and toxicity together in the one parameter. And again, this is the likelihood ratio based. And you can also optimize your approach by looking for those time administration, you know, this kind of parameters. So the other thing that, you know, once it's in the parametric family, then we can do a lot of things, like Barchoff-Lai and Narashan has this phase 1-2 trial based on generalized likelihood ratio, sequential. So they're testing the efficacy and the safety simultaneously. So that will be very easy to plug in there. And also we can optimize treatment plan, basically, depending on the goal. You can looking for long-term toxicity, or you know, you can change your length of cycle, you know, how long you treat them, how long you give them the break to optimize the probability, right? And those combination will be maybe easier if you have 2 doses, then you can say, okay, this toxicity depends on first dose, cumulative, second dose, and their interaction. I mean, just intuitively, you can do that. And also, you don't need, I don't need monotonicity anymore. I can change the, see if the green and the blue are different drugs. In this case, if if they apply at the same time, treatment 1, treatment 2, in the combination setting, I do have monotonicity, right? The more dose, the better. However, if I alternate one, I either use drug 1 first, drug 2, drug 1, drug 2, and the drug 2, drug 1, there's no order. These two are just 2 options, right? Just sequencingly different. So you cannot order them anymore. But by cumulative dose, we can calculate this. So that's the advantage. I think one partially the advantage of here is the biological relevant parameters. And you can calculate those stopping, continuing, all models. And so that's you can combine to put into phase 1-2 parametric format. Of course, there's still question. I mean, this is a hypothesis, right? Assuming that the incidence is driven by the dose, and I don't have data yet. I did ask for industry friends and see if they can provide some data. At least I can fit, you know, initially if there's possible, and otherwise it becomes mathematical exercise. And I have some hope because Chang's model actually fit EDO1 data pretty well, and also did for the AIDS very well. So it's possible there's some merits there. At least it's one for the approximation better than before. So I really think the take-home message here is we want to go maybe parametric because we are getting much more complicated problems than before. And we want to integrate PK/PD information into the those finding studies. Maybe we want to develop a model that the parameter, I mean, this is one of the models. It's not only model. So we want to develop a model that the parameter of the model has biological interpretation and help us to look into the structure or the relationship, okay? And also, we don't want fixed time because right now we pretty much focus on one time. And by doing that, we want to go beyond a fixed 4 weeks LTD and so on. So I recap, I did present some Bayesian decision theoretical design for single agent, for MTD and OBD, and also drug combination. And I also call for the research beyond empirical modeling of the data to be more parametric model, and Chang is one of the options. And partially, I think we are facing a lot of technical innovations. And so we really need to think about something beyond what we experience. So I wonder if we are ready for different kind of situation. In this year, just recently, there is a publication paper, one of the authors by Stanford, and they developed some kind of biosensor tool, actually can monitor or manipulate the dose in the body. So we're not talking about dose exposure. They can manipulate exposure directly. So here's an example that they had for animal studies. This was planned, and they actually achieved that exactly dose in the body. And so now this opens a lot of options. We eliminate one uncertainty from dose to the exposure, and maybe that will help us to do better in terms of design trials. And also we have all these called, it's still too early, like liquid biopsy and say real-time monitoring treatment effect, and how far we have. I mean, once, if there's that day that we can actually see the tumor response dynamic over time, or at least not all the time continuously, discretely, but many, many times, and what kind of design will we have? Will we still use the current design, or we should completely think about different ways? So given that, I want to thank you for listening. Right.
Was recommending randomized concentration trials.
Right.
Louis Scheiner back in the 1970s started by using nonlinear random effect models for dosing patients, and it applied to things like warfarin and so on. And I wonder if, to what extent you had a look in that literature as well for other examples of this sort of thing.
Yeah, I haven't really go literature in the oncology phase with that. That's partially I want to work with friends in that area. And it's hard to cross. I mean, early, maybe 10 years ago, there were a group of people from Amgen and us trying to form this called Pacific Ring Conference on Biometrics and Biostatistics. Pacifica, that was in the Cal Poly State University, where Cal lives. So that's why we had there. And unfortunately, they only had two or three meetings and stopped. And people involved left the area. But also, we didn't get enough interests. So it's kind of unfortunate. The dialogue is stopped there.
There were one or two statisticians who were sort of crossing the boundary, but the ones I all know of are now close to retirement. So Amy Racine-Kuhn was one who used to be involved in this work. Jerry Needleman was at Novartis, and John Steinberg again at Novartis. But it's sort of I feel it's a shame there's not more cross.
Yeah, no, I totally agree with you. I think, as I said, this is just one model. There may be better models that can fit in, and I really, yeah.
Some of the pharmacometric people have even moved on now to what they're doing is they're modeling the body as a sum of a dozen organs, let's say, which could include the liver, the skin, and things like that. And that's the way the thing is going. So they're going very much towards the sort of biological theory-based modeling of drugs.
Yeah.
I guess I have two questions. One, I guess, was on the PKPD stuff. I mean, I am not too familiar with it, but everything I've seen, there are these beautiful models, and then you try to, simulate off of them and compare it to the empirical data, and you just get total nonsense, unfortunately. When you maybe try to make it more complicated, I guess in your case, you're doing something quite simple.
Yeah, this is a first order approximation. So for the PKPD, you have blood, actually. You have evidence to say, hey, that's how blood absorbs, right? So this is a more theoretical assumption that toxin absorb into the body or the drug absorb in the body, right? I'm not talking about one organ, but use that as a parameter to approximate. Yeah.
And I guess the other one was early on you were talking about sort of maximizing this utility, and I think I missed this. Were you like coming up with a dynamic program that's maximized the whole thing, or using some?
Yeah, this is an explicit form, so you don't need grid.
I see, but you do. I mean, you're doing like the equivalent of activity in a bandit problem to get a maximized utility.
Oh no, not the whole. Yeah, not the end of the trial. We did look for first and second, okay. And the difference is small. whether we should go all the N patients, that's the goal. That was the original intention, that we want to put a simple model and potentially we can calculate that, right? But it turned out to be not that simple. Once you get second, third, second is not simple already, right? The first is very easy. And that's where we stopped. We didn't see the difference. Otherwise, we're going to pursue, yeah. Thank you.